What's up guys, I hope you all are doing well. Welcome back to my YouTube channel and welcome back to another YouTube video. In this video we will be looking at part 2 of our SciPy tutorial series that is within the tutorial series Scientific and Numeric Computing in Python. So you guys know that this tutorial series, Scientific and Numeric Computing in Python, is basically made up of two, sections. The first part, which we looked at and have completed, is the portion that dealt with NumPy. And now we are dealing with SciPy. So if you have been following along, you'd know that in the first video or the previous video, of the SciPy tutorial series, essentially what we did is we were introduced to just a bit of factual information that deals with the SciPy package, and we also got insight into how subpackages exist. Okay, and essentially we used a logical explanation. We said you can think of a package, okay, for example SciPy, to be a large container, and within this container we can keep smaller containers. Okay, and those smaller containers that house our code are referred to as sub packages. And essentially the main reason for this is having sub packages brings about a logical sort of segmentation of the package itself, so it makes it easier to access the portions of the code that we want to access. Okay, so in this video we will be talking about the concepts of optimization and minimization. I should mention to you, right, before we actually begin. So I told you initially, okay, you taking or making the choice to actually learn the SciPy package in Python is something that is very good. Okay, and also what's very important is that, honestly speaking, if you know for a fact that you will not be using the SciPy package for your job or career or field or so on, then honestly speaking, it is not compulsory for you to learn the SciPy package. Now, the reason why I am saying this is because the examples that we will come across as we gradually move on into future videos regarding SciPy, you'll notice that it demands or requires that you have some foundation of, I would say, high school mathematics. Okay, so we will be looking at the simple distributions such as a straight line graph and maybe a quadratic graph and so on. And essentially I will be providing us with the essential explanations we need just to understand what is going on, because the whole aim of this tutorial series is to take the mathematics that we are used to applying on paper, using a pen or pencil, and translating that into the appropriate Python code using the SciPy package. Now, this is a very interesting, concept itself to learn. So even if you are learning SciPy just, out of, I would say, a hobby of just building up on your Python knowledge, then yes, this tutorial is for you, and you will have a lot of fun and gain a lot of insight into the package itself. So I will create a new cell and I will just, comment down what it is we will be doing. So optimization and minimization. This is what we will be looking at in this video. The concept or procedure of optimization and minimization. Now, you may ask yourself, right? You may ask, exactly what is optimization and minimization? So essentially, minimization problems are a sort of category of optimization problems, okay? And the aim is, using SciPy, we have the ability to solve these types of problems quickly, efficiently, okay, effectively. Now, you may ask though, what is, when we talk about minimization, what is it? Okay, what exactly are we talking about? Now, just to give you a few examples of when this word minimization is used, essentially what we are talking about, or what we can talk about, is various different stuff. Okay, so if we want to talk about performing a linear regression sort of distribution, if we need to find the minimum and the maximum value of a function, the minima and maxima, if we maybe need to determine the root of a function, if we need to find the intersection points of two or more distributions, and so on. So those are just a few of the different, I would say, procedures that can be involved in your optimization and minimization problems. Okay, now you see, one thing that I should mention for these optimization or minimization problems, what we will use to help us, the sub package specifically, SciPy has an optimization package that is built, for us to utilize. Optimization sub package. The name of that sub package is optimize. So let's proceed to just do an importation. We can do from SciPy import optimize. So that's one way of doing it. Your alternate way would be import scipy.optimize as optimize. The preference is yours. Now, the first and foremost thing that I'd like us to, actually kind of experiment with, and just, kind of get a hands-on experience with, what we are doing is we are now modeling, kind of, I would say, real world data. Well, the examples I will be showing you is similar, but if you take these concepts and procedures and you apply it to your own data and your own real world problem, then you will find that they are very similar. Okay, the only thing that should change, logically speaking, is the data. The method or the technique in which we go about solving it is very similar, as you will see. I will provide us with I think a maximum of 3 or maybe 4 examples. We will see as this video goes on. So let's get to it. First, I would like to begin with a simple linear regression. So simple linear regression with SciPy. Now, what we will do is, this is the first example we are working with. Simple linear regression, you guys know, it's working with a distribution, or a function that basically uses an equation that is similar to y is equals to mx plus c. So that is there. Now, y is the y, or rather c is the y-intercept, y is the value itself, m is the gradient, and x is the x value. So let's proceed to utilize SciPy to actually work with this. So first things first, I would like us to head over to the importation statements. We cannot forget to import our NumPy package. As I mentioned before, oftentimes when you are working with SciPy, you will see that NumPy is also imported for use. And the reason is because we utilize some NumPy functions just to aid us in our, mathematical journey with SciPy. So one more importation that I would like you guys to do. As you guys know, we have matplotlib installed, which we did in the previous video. And I told you guys that don't stress if you never heard of matplotlib before, okay? Because the focus of this tutorial is not matplotlib. The focus is SciPy/NumPy. The reason why I, included matplotlib in this tutorial series is because, you see guys, we are going to be working with graphs, okay? And essentially, the way in which resources, or majority of the resources that I came across, the way in which they explained it is really just by giving textual explanations, and they gave us the Python code. Okay, now what I would like to integrate into this tutorial of ours is giving us the ability to actually view that graph. Okay, so one thing that's better than just viewing raw data is to visualize that raw data. Okay, see how it looks when plotted on a pair of axes. So that's why we have matplotlib. And again, I am reiterating, if it's the first time you are coming across matplotlib, don't stress. Really, you will see we just utilize about 2 to 3 lines of code from this package itself. Okay, so that's that. And in the future I will have a matplotlib tutorial up on the channel for you guys, so it is interesting stuff. Now, that was a simple discussion we had. Let's get to it. So the importations have been done. Now you see, one thing I'd like to mention to you, that there are several ways to fit data or to fit a linear regression kind of model to the data. Okay, and in this section, in this tutorial, what we will do is we will utilize the CurveFit method. CurveFit, that is the method we will be utilizing, and specifically we will be utilizing it from the optimize package. So instead of doing SciPy import optimize, essentially what this means is we'd have to do optimize.curvefit. So what we can do is, to make life easy for us, from SciPy.optimize import curvefit. There we have it. Now, moving on, let's get to the actual preparation and creation of the function, the equation basically, and the data itself. So what we will do is we will define a function, call it func. You may call yours anything you like. I will have the variables for the function set up as the parameters. So essentially, what you can do is assume, instead of using y is equals to mx plus c, we just have these different variables. Suppose we have y of x is equals to ax plus b. So it is the same, we just have the different variables for us. Now, this is the function itself, and for a straight line graph, essentially what is returned is the following. So return a multiplied by x plus b, and what I can do is enclose these in a pair of parentheses, so that makes sure that the multiplication will be performed first. Now, that is the function we will utilize. The next thing I'd like to do is the data. So we have a straight line graph that we need, or we'd like to work with, but how can we plot a straight line graph without the data points? Now we need data points, we need to generate some. So what we can do is we can use the numpy linspace function. This is a function we spoke about in the numpy tutorial series. It will generate numbers for us within the parameters that we provide. So essentially, between 0 and 10, I would like 100 numbers. And for the y values, what I can do is I will call a function, I will pass x, 1 and 2. So the gradient of this graph will be 1, the y-intercept will be 2. Now, you guys are probably wondering, what does this function look like? Let's plot this. We have x values, we have the corresponding y value. Okay, so what we can do is I will run this. I will let us view exactly what x and y looks like, just so we have some sort of idea, some sort of insight, and then we will plot it. So let's call x, that's x, as you guys can see. Now I will proceed to call y. So as you guys can see, this is y. We have the points, and it is uniform because of the fact that the linspace generated for us some evenly spaced values. Okay guys, so now that we have the data points, right, we have just looked at what the data points seem to be, and as we have seen in these arrays, we have some sort of idea as to how the data in our, we'll call it data set, is formatted. Now, to take things one step further, what I'd like to do is I would like to plot a scatter plot, okay, of the data points that we have, the x and the y, x, y, and below that I will say plt.show. You guys don't have to stress about this. This, as you know, is kind of extra information for this tutorial series. So I will now hit Control Enter, and as you guys will see, I am outputted with a visualization of the data points itself. Now, These are dots. It's not noticeable because of the size of the dots. But essentially, if I was to turn this now into a line graph, okay, now what I would like you to do or to understand is that you see, this is a scatter plot, okay, and a line graph is basically us joining the dots. And now in the scatter plots, the dots are kind of close by. So let's transform that into a line graph. And as you guys will see, this is the appropriate line graph. This is for the data that was generated by us, the x and the y values. Now, oftentimes we refer to data as this as clean data. Okay, so let me add a comment here: generating clean data. Now the reason why we do that is because, have a look at this visualization itself. Okay, this data is, in inverted commas, perfect, and in the real world we do not get perfect things that exist, especially data. Okay, data will not ever be in a clean or perfect format. There is always what we call noise in the data. So think of clean data as perfect data and noisy data as imperfect data. So basically now what we need to do is create some imperfections in the data. And the way in which we do that is by adding noise to the data. There's several ways to do it, right? Think about it. We have these y values, and essentially what we want to do is kind of fluctuate or bring about some sort of disturbance in the y values themselves. So we can randomly add, 0.5 or 0.2. We can just add random numbers to these values, which will cause them to be different. And the way in which we do that, or the way in which we implement that logic in Python, is to basically utilize a function from NumPy. I know we did not speak about this function before, but it is very easy as implied by the name of the function. It will generate random numbers for us. So what we will do is we will call this y of n is equals to y plus. So as you can see, I am adding 0.9 and I will multiply by numpy random dot normal, and within this function or method I will say size is equals to the length of x. So essentially what I am doing is I am randomly selecting a number from the length of x. I am multiplying it by 0.9 and I am adding it to y. That's giving me yn. Now, think about it. We spoke about NumPy, and NumPy allows broadcasting. Now, this tells us that, this will be applied for every element in the array of y, because y itself is an array. So, as you guys can see, this is what will happen. So, I can run this. I will let us view y. As you guys can see, that's y. It is still the same. And let's view y of n. And now, as you guys can see, there is variation in the numbers themselves. So that's that. Now, what I would like us to do is I would like us to view or visualize what the new noisy data looks like. So let's add a comment here. We add noise to the data below, as shown below. So we are plotting. So I will change this to y of n. So now what we are plotting is the exact same x values as before, but we are plotting the noise, the data points that have the noise. So the y values are different. And as you can see, the line graph now has changed. Initially, we were working with the clean data, which was giving us this very perfect straight line. And now we have noise in the data, which is telling us that, it accounts for the variation we see. Now, logic will tell us that if I plot a scatter plot of these data points, what I will see is that they are scattered in the similar manner in which the line graph joins, and kind of meets the points. So let me do plt.scatter And as you guys can see, this is the scatter plot. And yeah, it is very interesting stuff. So what I'd like to do now is, you see guys, the curve fit function, the most important one of this tutorial itself, it will allow us to fit a curve to data points. What this means is that given some data points without an equation, the curve fit function will attempt to find an equation that fits the data points. Now, let us proceed to see how this works. So given a function and given the set of data points, the curve fit function will try to find the values for the variables or constants of that function or equation. So let's proceed to logically implement what we just spoke. Now, one thing I should mention to you, right, is that the curve fit function, there are two important outputs that it returns to us, okay? It will output for us POPT and PCOV. For now, don't stress about PCOV. That is basically, as you can see, the covariance of the POPT array. POPT array is basically the optimal values according to SciPy that will fit the data points, okay, or the equation that brings us those data points. Now, if this does not make sense, don't stress. After completion of the example and after viewing the output itself, you will get a better understanding of what I am talking about. Now, one thing I'd like to do is, as you just saw, the curve fit function returns to us two outputs, POPT and PCOV. So we set up two variables and we call, or we set it equal to the curve fit function. Now what we do is we pass in the appropriate arguments for the parameters. There are three important ones: f, x data and y data. So I will space these out for you. So f is the function, in our case it is func, it's that straight line graph equation. X data will be basically the x values, y data, let's use the data points that have noise in it. Now when I run this, essentially what will happen is it does something in the background. A value has been assigned to PopT and PCOV. We basically have the covariance of the model. I told you guys, forget about this for now. This is something we can discuss at a later stage. POPT is much more important. So let us view this array. As you guys can see, this array has two values because of the fact that in our equation, we only have two variables. We only have A and we have B, okay, or I should say constants rather, okay. So essentially what this means is that according to SciPy, okay, SciPy did not know what the equation of this graph was. It made up its own equation given the function in raw form, given the data points for that function. SciPy has enabled us to create a complete equation by kind of filling in the blanks. What I mean is, we know for a fact that we were working with x1 and 2. Our equation we were working with is f of x is equals to 1a plus 2. Now, according to SciPy, SciPy thinks that, you know, it has not seen the function before. It only saw the data points and the nature or the type of equation we are working with, and it thinks that the optimal values for the distributions equation would be 0.9734a plus 2.0931. So as you guys can see, this is not bad at all, okay. SciPy has kind of effectively, it has done well, guys, because what we were working with, or the original form of the equation, and what SciPy thinks the equation should be, is very, very similar. So we can say we have some high level of accuracy. Now this if you are curious, this really is what optimization slash minimization problems are. Okay, it deals with stuff like this, but take it into perspective or context, right? This is just us working with a simple example to get some hands-on experience with SciPy. Now, in the real world, what would happen is you would be working with, I would say, actual data sets for your organization or company, and you would be attempting to find the optimal values for the equations to kind of fit your data to model your data. So again, I should mention to you, what we are doing here is very similar to the concepts of machine learning and data science. So SciPy itself is very powerful. Now, this was us working with a linear problem. Now, if you are curious, you may be wondering, what is it like to work with a non-linear problem, right? A non-linear optimization slash minimization problem. Now, that is the next thing we will explore. So, what we just did was a linear problem. As you guys can see, we have successfully completed it. Now, before we actually conclude on the first problem, what I'd like to mention to you is that matplotlib package allows us to plot more than one distribution or function on a single set of axes. Okay, so in the same way that we have the ability to take a pen and paper and we can draw more than one gradient or graph uh, on one Cartesian plane, what we can do is implement the same concept or logic using matplotlib. So now I would basically like us to have the scatter points with noise and the original straight line on the same axes. So what I will do is plt scatter x and y n, that's the scatter plot, and then I can do plt.plot x and y. Now when I hit plt.show, as you guys can see, we have the noisy data that is scattered and we have the perfect data that is in the form of a line graph. So that is interesting, and it's just good to know that matplotlib supports that kind of feature. Now, what we just witnessed was a straight line optimization problem. It is known as a linear problem. Now, in the real world, we hardly deal with or get data that is in linear form. I mean, data is messy in the real world, and oftentimes you'll find yourself looking at non-linear data. Now, what you may be wondering is, what is it like to be working with modeling an optimization problem that deals with non-linear data? So that will be the second problem that we look at now. Now, you guys know the equation we were working with in the first example was basically y is equals to mx plus c. That's the equation for a straight line graph. Okay, now the equation for a nonlinear function, I would like to utilize a function that I actually sourced from a resource. Now it is known as the Gaussian equation, okay, the equation for the Gaussian distribution, and that's what we will be working with. So I will type the equation out for you guys here, and it should take me a few seconds to do that. So this is the equation we will be working with. Okay guys, so this is what we have. This is the equation. Essentially we have a multiplied by the exponent of negative x minus b squared all over 2 into c squared. Okay, now in the specific Gaussian equation, a few things you should just be aware of is a is the scalar, b is the mean, c is the standard deviation. So that is just extra information for you to be aware of. Now, it's the exact same process as we did with the linear regression problem. Okay, the only thing that should logically change is the equation and the data. Okay, so let's go ahead and just model that quickly. So the function itself, now let's implement that function or that equation in a Python syntax. So we'll do x, a, b, c. Those are the three variables that we have to work with. Now this function will return, it's returning a multiplied by the numpy exponent, and within the bracket we have a negative x minus b to the power 2, and this is divided by 2 multiplied by c, which is basically our parameter, as you guys can see, and that is to the power of 2. So that is the equation we have for this function. Now the next thing we'll do is exactly the same. We will generate the clean data, exact same procedure, numpy linspace. You guys can copy and paste this if you'd like. So y is equals to the function. Now we are passing values for the function. Suppose we'd like to work with 1, 5, and 2. Essentially what this means is that a will take on a value of 1. So what we're saying is the scalar is 1. The mean will, let's just say we set it to 5, and standard deviation to 2. So that is that. Now yn, let's do this and then we will proceed to visualize what the data looks like. So let's add this time maybe 0.2 numpy random normal, and within this it's the exact same process. Size is equals to the length of x. So a random number will be selected, multiplied by 0.2, and we'll take that result of that operation and we'll add it to the y value for that specific element. That will bring about the fluctuations, which we basically call variance. So that's fine. Now what we can do is plt.scatter. So first I'd like you guys to view the original or the clean data. Let's visualize the clean data. We'll visualize it in a scatter plot first. What you guys will see is that it is in the form, or the shape rather, of a curve. I actually made a mistake here. I should have passed in x and y. So as you guys can see, that is a perfect distribution, and we rarely see that. Now if I change this to yn, the data points that had noise introduced to them, as you can see, it is now scattered all over the place. Now if I do a line plot of this, so let's do plt.plot within the noisy data. Let's bring back that perfect distribution in the form of a line graph. So this is what we have, as you guys can see. And I should reiterate, just to remind you, this is the Gaussian equation, okay, the Gaussian distribution. Now moving on, it's the exact same process, guys. What we will proceed to do is, let me comment this out so I don't keep, getting a visualization. And POPT PCOV is equals to CurveFit. And once again, guys, it's the exact same process. What's going to happen now is that when I run this, I'm going to pass my parameter, I'm going to pass my arguments to my parameters, and when I run the script, SciPy, or the CurveFit function rather, available from SciPy, is going to just have a look at the data points that we have passed it. We have passed it a function in raw form, and it will attempt to find for us values for that function, okay, constants that fit the function itself. So let's proceed to pass it in. So f is equals to func, that's the function we are using. The x data should be x and the y data should be that data or that array that had noise introduced to it. Now I am going to run this and let's view from within the IPython console. Once again, you guys can see and view the covariance if you'd like. You guys can read up on that. I am not going in depth into that. In fact, I am not going to talk much about this. What I am interested in is PopT, because for now that's the most important thing we need to understand. Okay, PopT, when I press enter, it's going to give me an array, and that array will be containing three values for the three constants in the function. It's going to tell us, SciPy will tell us what it thinks the scalar should be, what the mean should be, and what the value for the standard deviation should be for that equation. It does not know the equation we looked at, but it has access to the data points that arose as a result of that equation. So PopT, as you guys can see, essentially SciPy thinks that the values are 1.08, 5.078, 1.903, and that is not far off from what we are actually working with. Okay, we are working with 1, 5, and 2, and so there is some sort of variance in the output itself. Now that is interesting. What you can do, okay, what you can do is actually take these values, substitute it into the equation, and generate yourself an array of values, an array of y values with the actual y values for the distribution. And what you can do is plot them side by side, just to get an idea of what the original equation looks like and what SciPy thinks the values are. So that is interesting. Now what we just worked with is an example that demonstrates how we actually proceed to solve a minimization or optimization problem using a nonlinear, we'll call it data set. Okay, what we've just done is we've fitted a curve to a nonlinear distribution. So that is interesting. Now I can comment this out, so that's fine, or rather I'll just create a new cell. That's what I did. Now before we actually end this video, right, so I told you guys I'll give you guys 3 or 4 examples. I'd like to just give one more. This I would say is, in inverted commas, the most difficult one we will see, and it is the last problem or optimization problem for the video, for this video. Essentially this is extra information just for you to have an insight into how extravagant we can get with the SciPy module, right? What we've just worked with, you guys will agree with me, we've worked with 1D arrays, okay, one-dimensional data sets. Basically, there was not much difficulty with modeling that linear regression and the Gaussian equation. Now, if we take this one step further, okay, you may ask now, what is something I would say difficult, something more extreme that NumPy can handle, okay, specifically with regards to the CurveFit function. Now, to take this one step further, for this last problem, this will be the final example of optimization that we will deal with for this video. Now, to take this one step further, what we worked with in the initial 2 problems was just a single equation, okay, but going one further, we have the ability to fit the one-dimensional data set, and we can do it with or using multiple equations. So specifically now, suppose we have 2 Gaussian equations, okay, 2 Gaussian equations that have different variables. Now, what if we take these or this equation and we fit it to our data? Essentially, we are going to attempt to fit multi-dimensional data. Okay, we have multi-dimensional data and we are attempting to fit a curve to that data. Now this example, what you will see And remember guys, this is all additional information. You can end the video right here. The third problem is not compulsory for you to see, but if you are curious as to what SciPy can do, then go ahead and enjoy the video. So what you are going to see now is what's called fitting line spectra. This is what we are going to do. Fitting line spectra in simple terms. As you saw earlier, we were working with a Gaussian equation, a Gaussian distribution. Now, fitting line spectra is when we have the ability and we actually proceed to fit a combination of Gaussian distributions, or curves rather, to data. That's really what it is. Fitting two or more Gaussian distributions to the data points. Now, let's proceed to do that. So what I will do is I have the equation copied already, and I will just paste it on the screen for you. So I want to avoid making errors in the equation, or the typing of the equation rather. So as you guys can see, it is the exact same equation as before. Essentially what you can do is copy this equation here, copy this portion and paste it, and add an addition sign in between both of them. Okay, so coming back to our example, what we now have to do is we have to generate the clean data. So we go about doing that, in the way in which we have been doing all along. Now we will add a comment here, generating clean data. Let's suppose we are generating maybe this time 200 values. We have been working with 100 all along. So let's have a deviation from that. 0, 20, 200, and for the y values I am going to call my function and I'm going to pass values. So suppose I would like the function itself to be having the following. So it will have x, and the values I'd like to pass to my function. Suppose I would like to have the values 1, I would like to have maybe 3, 1. Let's do a negative number, so -2. We'll do a 15 and maybe even a decimal, 0.5. Now that itself is the clean data. To introduce variance into the data points, what we can do is the exact same procedure as before. I will add, let's say, 0.2, and then I can multiply, suppose by numpy.random.normal, and within this I will say size is equals to the length of x. Now before moving on any further, what I would like us to do is visualize this data. First things first, let's visualize the clean data. So we will scatter x and y. As you guys can see, we have a multi-dimensional distribution here. Now if I visualize the data that has noise introduced into it, you can see it is having much more variance. Now, the next important thing for us to do is to actually proceed to utilize the CurveFit function. Now, before proceeding to type out our PopT and PopCov, there is one thing I'd like to mention to you. We'll need to utilize, or rather we need to pass a value or an argument to another parameter in the CurveFit function. When we are attempting to do something similar to line spectra, which means basically fitting two or more Gaussian distributions to a set of data, what we'll have to do is, using the CurveFit function, we'd have to provide SciPy's CurveFit function with guesses as to what we think, the values of the constants in the equation are. So for guesses, suppose we are doing 1, 3, 1, 1, 15 and 1. As you can see, it is not 100% similar to what we have up here. So that's what we think the values are. This is why it is guesses. Now I will do CurveFit f x data, y data, and the one parameter that you are not familiar with is p0. Now if you guys see, p0 is defaulted to none, as you will see. Let me bring that up. as you can see, f x data, y data, p0. P0 is an array that is going to take the guesses for you. It is defaulted to none. So let's pass arguments to these parameters. Okay, so I can do f is equals to func. X data will be x, y data will be the noisy data, yn, and p0 will be guesses. Now, if I do PopT PCOV, oh, actually now I am prepared to print my array to the screen. Forget about the covariance array for now. For now, focus on the array of the optimal values for the variable. So I do a print, and as you guys can see, I have my 6 values for my 6 constants for the equation as estimated by SciPy's CurveFit function. We assume that the guesses we have are 1, 3, 1, 1, 15, and 1. And SciPy has succeeded in catching that negative value that fits the data equation. So as you guys can see, this is what we have. Essentially, what you can do to make this more interesting and to have yourself a kind of line of regression, what you can do is print, or rather substitute these values into the equation, generate an array of the accurate y values for the corresponding x values for this distribution, and you can plot yourself a line that runs through those data points. So that is interesting. I do hope you guys found this video interesting as much as I did. Honestly, it is very fun making these videos for you because I also enable myself to learn quite a bit. So with that, guys, thanks for watching. Thanks for staying till the end of the video. Good luck with your work, and I'll see you in the next YouTube video.